The topic of my talk is, again, deep learning, but with a different framework called Keras. I'm a senior research engineer here in Netherlands, in Eindhoven. And this is the outline of my talk. So I will try to briefly introduce what is deep learning, very briefly, because people have talked about it before, and Keras. I will introduce here, which is a data-driven location service company where I work at the moment, and of course I should speak about them because they are sponsoring my trip. I will talk a bit about the research activities that we do in the company, and then I will try to give some use case of deep learning that we use in the company, but just bear in mind that all those use cases will be like dummy. Those are not the actual one because there are lots of issues with data privacy and other things. So those are just self-made projects or self-interest, but aligned to the company direction. So starting with deep learning, what it is, and why do we think it's better than other methods on certain types of data? It's quite simple. In a nutshell, it is a neural network with lots of different layers in between input and output. And the series of layers between the inputs and outputs do all these different things like feature identification, engineering, whatever it needs, and process a series of stages based on how many layers you do have, just like we do with our brain. So it's neural network, or a multi-layer neural network, which was there for 30, 40 years. What's new? There are two things. First, we always had good algorithms for learning neural networks having only one hidden layer. But those algorithms did fairly poor when there were like multiple hidden layers. So the new thing is we have algorithms that train the multi-layer networks pretty well. And the second thing, now we are always talking about big data, huge amount of data from users. It's like the era of data explosion. So whatever algorithms we have, we can really test on a huge amount of data. So that's also something present these days which were not there before, 30 or 40 years, or even 10 years back. So a little bit about Keras. It is developed by François Cholet from Google. It's a minimalist Python library. It can run on both Theano or TensorFlow. So it's practically an API or a front end, and these Theano or TensorFlow, it's the backend thing. So it's very simple to use. You can develop prototypes pretty fast, and you can test it. It works with both Python 2.7 and 3.5, and it can run both on the CPU and GPU. It's quite simple to do that. Some interesting facts or stats about the library. So these stats has been gathered by the developer himself, François Cholet, and posted in Twitter. So in terms of number of forks, it comes third after TensorFlow and Caffe. Both are quite famous. In terms of issues opened, it comes second after Caffe. That means it's quite popular, so people are finding bugs and trying to solve it. In terms of GitHub contribution, it comes fourth after Theano, TensorFlow, Caffe. Theano is the oldest deep learning one. TensorFlow is supported by Google. And there is Caffe. Caffe is also quite popular. So after all these three, I think it's quite a good achievement by Keras. And since it's also kind of new. So overall popularity, I don't know how he got these numbers for this empirical calculation. It comes third, but it makes sense. A little bit more. So it's again a lightweight API. It provides a consistent interface to different backends like Theano or TensorFlow. And it's really easy to change this backend. So you have this JSON file, a configuration JSON file for Keras. You just change the backend from Theano to TensorFlow or TensorFlow to Theano. And again, there is also another configuration file where you can just choose GPU or CPU and how much memory you want to use. So it's quite straightforward to configure this library. Some simple flow of building a model with Keras. So you have to first define the model, which is a sequential, means you create several layers. So input layer, then several hidden layers. It can be many different things. I'll come to that part later. And then once you are done with defining the model, you compile the model. So you need to specify what should be the loss function, what type of optimization you would like to use, and then you have to compile that one. Then, of course, once you compile the model, you have to fit the model. And then you can do prediction based on predict function or evaluate your model on the cross-validation. Some of the layers of Keras. First is the dense. That means all the nodes are connected to each other. You can do many different things. You can initialize the weights using uniform distribution, or there are many advanced, like here I use Glorot, where it's also a Gaussian distribution, but you just rescale with fan in, fan out. Then you have this LSTM, or recurrent neural network. You have GRU. Similarly, you can work with convolution, one-dimensional or two-dimensional. Again, there are lots of hyperparameters that you can tune inside, quite straightforward to do that. There are also others which I didn't put there, but if you're interested, you can go to the website of Keras. They have a very good documentation. So you have dropout layers so that you can reduce the number of nodes. Of course, you remove the edges as well to reduce the overfitting as much as you can. You add noise layer. You can do that just to check the robustness of your model. You can do pooling so that you can subsample your data, and you can, again, get rid of this overfitting, as well as you reduce some computation complexity or computation time. You can normalize. You can do embedding. Embedding is mostly for NLP, like when you have this word-to-vec and other thing. You want to do text processing, you convert them into vectors of numbers. So for that, you can use this layer. You have most of the activation functions there, which converts the input, with a transfer function. You have sigmoid, you have hypertangent, you have ReLU, soft plus, sigmoid, all these things, and you also have advanced activation layers as well. You have different types of objective functions, like you can optimize against loss, different types of loss, root mean square error or mean absolute error. You can deal with binary cross entropy, of course, depending on what you want, classify your regression. And you can optimize all those loss functions using stochastic gradient descent, or RMS prop, or Adam. There are lots of options there, and you can just do it pretty easily. I will demonstrate later on. So this is Keras in a nutshell. Now I would like to talk a bit about the company, and then I'll come back again to Keras. So it's like going back and forth so that we keep track of both. So here is a company which mostly I think nobody knows, because we always stay in the behind. So we have been doing maps for more than 30 years. We have mapped around 200 countries, and millions of changes are pushed into maps every day. And it's not a very small company, so around 7,000 people working there. And maybe you know about Navtech, which used to be the name previously. So if you see into the in-car navigation system in North America and Europe, 4 out of the 5 is built by us. So even not many people knows about here, but people have been using it for quite some time. So what we do, we try to make sense of the world based on location data. So we try to find how can someone move safely from location A to B. Then how can you measure infrastructure properly based on location data? Optimize business with many different aspects, of course, with location data. We built our first, so this is the roadmap of here, how it evolved and where it is now. So we built our first map of California in mid-80s. Since we have been, it's almost like 30 years, and from then we have mastered how to develop maps for cars, for wave, for mobile. We have been using maps as an instrument for making sense of the world, always carrying conveying information. So what we are interested, so it started with how can we reach from A to B. Then it became, once you can reach from A to B, what is the fastest route? Then it became, what is the next point of interest? So is there any gas station nearby? Is there any restaurant nearby? All these things. But things started to become more and more complex over time. For example, if you're thinking about package delivery. So if there is certain change in the road, like heavy rain, how long will it going to delay the package delivery? If I'm driving, how much charge do I have in my battery to reach my destination, considering it's a hot day, so I have my AC on in the car. So all these different things. again, people have been talking a lot about autonomous driving. So if I have an autonomous vehicle, how can I make sure that the way the car is driving is acceptable to me? Or when it has to park somewhere, is it doing it properly? If I want this car to park by itself, how do I know there is enough parking space for the next couple of minutes? So all these different things. So as more and more vehicles or devices are getting connected, and the amount of data they're generating, the questions are becoming more and more complex. But of course, we know these things, and that's not actually a problem. It's rather an opportunity. So we always thought that maps are the ways to detect the change in the world. And the more and more data source we have, it's easier for us to detect the changes. And there are endless ways we can do use of this data. And that can be used for everyone, by people, for business, everything. So for several years, we have been developing this location-based platform. So it's for cargo, for like healthcare, for many, many different things like car share and everything. And this platform that we developed has been used by many different companies like Facebook, Amazon, different cars like BMW, Mercedes, Audi, and all those guys. Now, a bit about the research that we do here in the company. So this is a map, example of a next generation map. So it's totally different from that we had in the historical data of mapping we had previously. So you can see that you can even see the elevation of the buildings in the maps, and all are automatically generated from some image, from aerial image data. And it's, by the way, Boston. Now, these are some of the representation you can do. So first one is trajectory, like when a car moves, you get all this information from the sensors, and then you do trajectory analysis, but you have to visualize, which is quite important. The next one is the next generation mapping. Then third one is point cloud analytics. So all about mapping experience that we try to do. And we need to be accurate. And since we are talking about high definition mapping, autonomous vehicle, we can't afford to make too much of mistakes. So at the moment, the accuracy is in centimeter level, but we are trying to make it even more accurate. Some of the technology that we use, one of those was LiDAR. That means we use a laser, and we send light, and that reflects, and we measure distance. It's very accurate, but it's very expensive as well. But these are some of the technologies we try to use, and then we color code and try to get a map out of that. So in essence, everybody is connected with multiple devices, and that leads to the Internet of Things. So we are generating data. The machines are generating data. It is structured and unstructured. And so in essence, we are getting huge volume of data in a very high velocity. The data is, there are a variety of data. It has variability, it has visualization, so it has got value. And we have to use that one somehow. So that means that they gives us activity, people gives us activity measure, which are geospatially located, which are our point of interest. And all this data allows us to discover and build model which helps us to predict activity. And then, of course, this is like a network. So you have Internet of Things, big data analytics, and it has to be localized from person's context. So again, maps are changing. They're becoming companions, advisors, devices are listening, reporting, and tracking. This is Eindhoven, where I stay. It's a very accurate map, and these different colors are actually showing the traffic. So when it's red, it's high traffic density. That means the vehicle is running very slowly. So this is something we try to analyze with the mapping data and then try to visualize, of course. And this is what we get, again, with analytics. So we try to get the stay time. So when there is a red, that means a vehicle is staying for quite some time. So we use it to find points of interest. So if you see that there are lots of red dots towards the center, that means, I think, Phillips Museum is there, so people spend some time. There is some shopping malls as well, so people park their car and spend some time. So with the mapping data, we try to find points of interest. That's one example of some analytics that we try to do. Next is some vehicle analytics. So for example, a car is driving around 50 or 60 kilometers per hour. Then there is a curve in the road, and then most of the cars brake at that point. Some car, very few, brakes on the second point. So the centroid is always on the first one because most of the car does that there. So the first one is normal behavior, and the second one is not. So if you brake in the second point, there are quite a high chance with a high speed that you might cause an accident. So these information are quite valuable for different customers. For example, if imagine some insurance company who are like wants to know how people drive, and based on that they want to set the premium. If they get hold of this data, they can set it accordingly. So this is kind of analytics lots of people, lots of players are interested in. And of course, you can also use that to create a driving assistance system. So whenever someone is missing the first point, you can create an alert saying that, okay, you missed the braking point, be careful, do something now. Another example, people are driving through the road, so the white splines representing the curvature of the road, and the green ones are implying the lateral acceleration. So that's for a normal situation. Now, when there is rain, of course, it should reduce. So again, it's based on weather data, you are creating some alert that you are driving at this speed with this acceleration, so consider reducing it because it's rainy, it's slippery. So there has been some shift from cloud computing to edge computing. We are also working on that. So you don't send everything to cloud, rather you compute in the edge, aggregate, and then send back to cloud. So that's quite interesting work that we have been doing at the moment as well. So this one will try to give this example. So it's a video, I'll just let it play. So I guess you have some idea about what type of thing we had been trying to explain with this one. Now, again, coming back to deep learning and Keras, and of course, some notebooks at the end. So first, I will try to give an example with image classification. So our point of interest is to do vehicle type classification from the perspective of autonomous vehicles. So when a vehicle is driving, it tries to identify something that is going in front of it. So based on whether it's a truck or some other automobile, it will change its driving behavior. Again, it's a very simple example that I'm going to present. It no way reflects what we have been working in the company. It's just some simple use case. So the GitHub link is here, so you can find all the codes there, but I will anyway go to this one. How do I? So, like normal thing, I imported all the different functions from Keras.
Sorry, could you please zoom in to make it more readable?
Yeah, let me try.
There should be command plus.
Yeah, I'm just trying. Is it okay now?
Yes.
Okay, maybe a bit more. So I'm using Theano backend here, and I'm using a GPU, which is a NVIDIA Quadro M4000. And the batch size I have been using is 32, number of classes 2. So it's a data set I have been imported from Cipher 10 database, which has got, I think, 10 different classes. But I'm just choosing the automobiles one. One is normal vehicle, another one is truck, because I'm interested in that data. So the batch size is 32, number of class 2, as I told. Number of epoch is 20. It's just a very small number. You would definitely like to do with a much bigger number for bigger data set and more complex data. But this is just an example. I'm doing data augmentation, which will come later. So this is the original data set with 50,000 training and 10,000 test samples. So what I did, I just took the class 1 and class 9, which is automobile and trucks. Then I took only that part. So from 50,000, it's now 10,000 train samples and 2,000 test samples, only with automobiles. Then I converted those into categorical variables for the prediction. So this is how the image looks like. The first one is an automobile, second one is a truck. So of course I did some data pre-processing, so I converted them into float. Then I had to divide by 255 to just convert into RGB between 0 and 1. I did a little bit of data augmentation. That means I just commented all of those. So that means setting input to 0, mean to 0 for the data set, sampling, dividing by standard deviation, all these different normalization stuff. So I did it for the real-time data augmentation. So once that data augmentation is done, I define the network using Keras. So it's a sequential network. All the Keras networks are sequential. You have to start with that part, then you keep on adding layers. So I added a convolutional 2D network, because 2D layer, because it's a two-dimensional input, height and width for the image, and it's 3-channel because it's RGB. Then I did activation layer. I added one more convolution layer. Then I added max pooling, like I tried to explain before. So this is the model that I used. Then I activated the model using stochastic gradient descent with these parameters. Then I had to compile against the model against loss, which I used as categorical cross entropy, because it's good for binary classification. And I estimated accuracy as a measure. So then after doing that, I fitted the model. So it's a small data set, and I had a GPU, so it ran quite fast. So you can see it's like a few seconds. Once that's done, I wanted to, you can see the accuracy it reached for the training data is around 0.9, so 90%, and for the validation data is also it's 90%. So I checked the performance a bit more. So I checked different things like precision, recall, F1 scores, so all are in the range of 90s. The AUC is also around 90s. So you can check the ROC curve here, which is true positive rate against false TPR against FPR. Then this is the confusion matrix, you can see. So most of the time it's predicting automobile as an automobile, truck as a truck, and in very few cases otherwise. So false positive rate is quite low. In Keras, you can save the model quite easily in a JSON format. So you can save the architecture and you can save the weight. So once I did that, I imported separate images from the web. So these are 2 images, one for car, which is quite nice, and one for truck. But in order to fit them into the model, of course, I have to rescale it, because that should look quite crappy, as you can see. So I rescaled, and now it looks like this in order to feed into the network. So then I just called the model directly, and it predicted first one to be 0, which is an automobile, second one to be 1, which is a truck. Now just one simple example. So if you have saved the model, it's quite easy to import the model. So the first one is load model. So you can import the model from JSON, and you can load the weight as well, and then you can classify. So it's quite fast. So once you train the model, you can use it easily in the production. Just you have to call the model and do the prediction in real time. It's possible. So that's first example where you can do some object recognition using Keras. The second example I will give is about sequence prediction with the same library. So again, I'm using Theano backend with GPU Quadro M4000, and it's for bike sharing. So I will try to predict how many bikes are going to be shared in next some time window. It's important from our perspective because, for example, it can be related to the amount of places there for parking, or even if it's, bike rental is important from mapping perspective as well. So I'm driving, and then I wanted to find that if I want to rent a car from some places, a bike from some places, what's the possibility that within next 1 or 2 minutes I can have some bikes there. So I downloaded this data from UCI, which is quite well known. Some of the previous speakers also use this data set from there. So I loaded using pandas, and converted again into float. Then I rescaled it. So this is how it looks like. So these are the days numbers versus the number of rentals normalized. I split it into train and test. So 70% for training, 30% for the test. Then I converted that into a matrix with some window. So the data, after setting the data set, I created the model, which is again a sequential model. Then I added an LSTM layer. So LSTM is abbreviation of long and short-term memory. So it can capture the time dependency of a time series pretty easily. So that is why it is quite useful if you want to predict a sequence using Keras or whatever library you want. Then I added a dense layer. I considered mean square error as the loss because I'm again doing here not a classification, rather regression, Adam optimizer. And then I ran it for a window of batch of 1 sample and 100 number of epochs. Then you can see that loss is quite low. Then I check the accuracy of it. So the root mean square error for the training is 959. Testing is 1351. It's not that easy to interpret because these are rescaled, so it's not between 0 and 1. So that's why I just plotted. So the blue is the original data set, and the green one is the reconstructed data set for the training part, and the red one is the reconstructed data set for the testing part. So you can see that for a given time window of 1 unit here, you can try with higher values as well, of course. It predicts the trend quite nicely. So again, just to put emphasis that it is not exactly what we do, it's just some simple example I am trying to present that you can do with this library. So these are the libraries I wanted to show here. And so yeah, so these are the 2 things I wanted to show for what you can do with Keras. There are many different other things that you can do. You can go to the library, and they have lots of examples there from different perspectives, not only image processing or sequence prediction, but there are also text analytics and lots of different things you can try yourself. So that's it. Just some small note. We are also hiring. So if you're interested, you can check our website, or if you're looking for a research position, just drop me your resume to me if you have any question.
Yeah. Just wanted to know about the data set. So when you have like 2 classes for automobiles and trucks, when you filter from the CFR data set, so how many samples do you have for training your deep learning model?
10,000 for the training, and I think 2,000 for the testing. It's there in the notebook.
Oh,
it's quite small for deep learning point of view, but as I told, it's just to demonstrate what you can do.
Oh, okay, thanks.